Hi, I'm Ben-Yaakov. This is a riddle about capacitor charging. It was motivated by a question I got from this YouTube username. We're talking about charging a capacitor, and I'm showing here a sequence of charging and discharging of a capacitor through a resistor to a voltage of V in. We know that the energy stored when fully charged will be CV squared over 2, and then the energy lost in the resistor or dissipated by the resistor during the charging will be V squared over 2, and the same thing goes during the discharge because all the energy is actually lost to the resistor. So the total energy dissipated by the resistor will be the sum of these, and the power in the resistor will be this sum here times the frequency of these pulses. So now I'm running a simulation in LT Spice. I have here a demo circuit. This is a pulse source, 10 volt pulses, 50 kilohertz. There is a rise and fall time. In this particular case, the first one I'm showing, the rise and fall time is 1 picosecond, very sharp pulses. And we have 10 ohm here and 1 nanosecond, so the time constant is very short. Now we understand that the total energy dissipated by the resistor is CV squared over 2, and then times the frequency is the power loss. And for this particular case, this is a 10 volt pulse and 1 nanofarad capacitor. We end up with a power dissipated by the resistor of 5 milliwatt. And here is an example of the charging process, the momentary power. This is the voltage times the current of the resistor. This is the momentary power, it's fairly high. And then we have a charging of the capacitor, and the time constant is short because we have 10 ohm and 1 nanofarad, so it's about 20 or something like this nanosecond. So this is the process of charging. The discharging will be similar to that. And lo and behold, if we look at the average of the product voltage times current of the resistor, we get the expected 5 milliwatt. Now I'm changing the resistor to 1 kilo. Now we know that this should not make any change. The power loss should be the same. So let's have a look at it. Again, the only difference here is that now the resistor is not 10 ohm but 1 kilo ohm. And here is the charging front end. In this case, the maximum power here, momentary power, is much lower because the resistor is high, so the current is much lower. And still, we do have an average power dissipation in the resistor of 5 milliwatt. Now comes the strange part. Leaving the resistor at 10 ohm, I'm now changing the rise time and fall time, because this is the same number here for the rise time and fall time, from 1 picosecond to 1 nanosecond. And strangely enough, now we have a different power dissipation. It's 4.8 rather than 5. It's about 3% less. And the question is, why is it that by changing the rise and fall time, I'm getting, in this case, a lower power dissipation? What's the reason for that? I'll be happy to get your answers. I'll try to respond to all your comments. I may not be able to do that. A full answer and explanation will be given in a forthcoming video. Thank you for your attention.